Let us see some application of moment of inertia. For example, moment of inertia of a ring about the axis passing through its center and perpendicular to its plane. Also, we'll see the moment of inertia of a uniform disk having a radius r and about an axis passing through its center and perpendicular to its plane. An object is called as a uniform ring if its mass is practically situated uniformly on the circumference of a circle as shown in figure. It is a two-dimensional object. Consider that it has a negligible thickness. It is rotating about its axis, passing through its center and perpendicular to its plane of circle. Let its mass or entire mass is m, which is practically at a distance equal to its radius r from the axis. Hence, the expression of the moment of inertia of a uniform ring of a mass m and radius r is given by I is equal to mr square. Moment of inertia of a disk. Disk is a two-dimensional object and negligible thickness. It is said to be uniform if its mass per unit area and its composition is same throughout. If it is rotating about its own axis, that is passing through the center and perpendicular to its plane, its entire mass m is practically at a distance equal to r to its radius from the axis. Hence, the expression of moment of inertia of a uniform disk of a mass m and radius r is given by I of uniform disk is equal to half mr square. Derivation of moment of inertia of a uniform disk. Consider a uniform disk of mass m and radius r about its own axis, which is the line perpendicular to its plane and passing through the center of this circular disk. The surface density of a uniform disk is given by mass upon area. Area of a uniform disk is given by pi r square. So we can write the equation as m upon pi r square. The uniform circular disk consists of number of concentric rings of radii increasing practically 0 to r. Let one of such ring of a mass dm is shown in shaded portion in this figure. The width of this ring is dr and the radius of the ring is small r. The width is very small, it's nothing but it is a negligible. So the radius of this entire ring will be considered as to be average radius r, that is a small r. The area of this ring A is given by pi derivative of r square, and if you solve this derivation, we will get the answer is 2 pi r into dr. The surface density of a ring, we know that the mass upon area. We are going to calculate the surface of this small shaded portion ring. So we can write down the sigma is equal to m upon a. This m is a mass of this smaller shaded ring, that is dm, upon area of this shaded region ring, it is 2 pi r into dr. So just calculate the value of dm from this equation, and it is nothing but sigma 2 pi r into dr. So as it is a ring, this entire mass is at a distance r from the axis of rotation, and therefore by the definition of moment of inertia for such ring is given by small, that is IR is equal to small mass into r square, that is a dm into r square. So the moment of inertia of a disk is now can be obtained by integrating this I from its radius ranging from 0 to capital R. Continuing the same, the moment of inertia of a uniform disk, that is the entire disk, is given by I is equal to integrating I small r, where limitation is ranging from 0 to capital R. Just substitute the value of I small r, that is equal to integration of dm small r square, where integration is ranging from 0 to capital R. So just substitute the value of dm in this equation. We can write the value as integration sigma 2 pi r into dr r square. Integration is ranging from 0 to capital R. Take the constant term out of this integration, and we can write the value as sigma 2 pi integration of, here r square into r can be written as r cube into dr. Integration is ranging from 0 to capital R. Just solve the integration part, and we can write the equation as sigma 2 pi into the bracket small r raised to 4 upon 4, close the bracket, give its limitation value 0 to capital R. Solve this limiting that is a definite integration, and we can get the value as sigma 2 pi into the bracket. We are just substitute the upper value of this limiting in this calculated part, and therefore we can write here capital R raised to 4 upon 4 minus, then substitute the lower value of this integration in this calculated part. So that value is 0 raised to 4 upon 4. Close the bracket. Now this 0 raised to 4 upon 4 becomes 0, and we get the value is sigma 2 pi into the bracket capital R raised to 4 upon 4 minus 0. Complete the bracket, and we get the value is sigma 2 pi capital R raised to 4 upon 4. Now further integrate that, solving this equation, we have to substitute the value of this sigma in this equation. Now this sigma value we are going to put it for the entire uniform disk, and therefore the value can be written as 2 pi into m upon pi r square into r raised to 4 upon 4. Now just cancel out the some terms here, that is 2 1s are 2, 2 2s are 4. Also the r factor is getting cancelled out here. R square from the denominator will get cancelled out, and numerator will get the r raised to 4, sorry r raised to 2. And if you just find out these values, you will get the answer is nothing but I is equal to half mr square. So this is a moment of inertia of a uniform disk. In this way, similar way, we can find out the expression for moment of inertias of objects of several integrable geometrical shapes can be derived, and some of those are given in this table. The expression for moment of inertias for some symmetrical objects are given here. The moment of inertia of a thin ring or a hollow cylinder about its central axis is given by I is equal to mr square, where m is the mass of this thin ring or hollow cylinder and r is the radius of this hollow cylinder or thin ring. The moment of inertia of a thin ring about its diameter passing through its center is given by I is equal to half mr square, where r is the radius of this thin ring. The moment of inertia of a annular ring or the thick walled hollow cylinder, this is the thick wall hollow cylinder about its axis passing through its center is given by I is equal to half m into the bracket r2 square plus r1 square, close, close the bracket. Here r1 and r2 are the inner and the outer radius of a thick wall hollow cylinder or an annular ring. Moment of inertia of a uniform disk or a solid cylinder about its central axis is given by I is equal to half mr square, where this axis is passing through its center of this solid cylinder. Uniform disk के लिए the moment of inertia of this uniform disk about its diameter passing through its center is given by 1 by 4 m r square, where r is a radius of this uniform disk. The moment of inertia of a thin walled hollow sphere about its central axis passing through its center is given by 2 by 3 m r square, where r is the radius of this hollow sphere. Moment of inertia of a solid sphere about its central axis passing through its center is given by 2 by 5 m r square, where r is the radius of this solid sphere. Moment of inertia of a uniform symmetric spherical shape about its central axis passing through its center is given by 2 by 5 m into r2 raised to 5 minus r1 raised to 5 upon r2 raised to cube minus r1 raised to cube, where r1 and r2 are inner and outer radius of this symmetric spherical shape. The moment of inertia of a thin uniform rod or a rectangular plate about an axis passing through the center and perpendicular to its plane or the length is given by 1 by 12 m into L square. L is the length of the rod or the length of a rectangular plate. The moment of inertia of a thin uniform rod or a rectangular plate about the one end and perpendicular to its length is given by 1 by 3 m L square, where L is the length of this rod or the rectangular plate. Moment of inertia of a uniform plate or rectangular parallelopipe about its central axis passing through its center point is given by 1 by 12 m into L square minus B square, where L is the length of this parallelopipe and B is the breadth of this parallelopipe. Moment of inertia of a uniform solid right circular cone about the central axis passing through the center is given by 3 by 10 m r square, where r is the radius of this cone. Moment of inertia of a uniform hollow right circular cone about its central axis, which is passing through its center, is given by half m r square.